So now for a matrix, the trace of a square matrix is just the sum of the diagonal entries. So sum k equals 1 to n, and then the diagonal entries are akk. So we'll see shortly that the trace of an operator is equal to the trace of the matrix of that operator. And that's independent of the choice of basis in which this matrix is expressed. In order to prove that, we'll need the following lemma or theorem. So this is 10.14 in the book, and it states that for two matrices of the same size, the trace of AB is equal to the trace of BA. And so for that, we just need to look and see what's on the diagonal. So the jth term on the diagonal, so the jth diagonal entry of AB. So if we go back to what the matrix product formulation is, see, so we're going to do AJK times BKJ and sum that k equals 1 to n, and that'll be the one that's in the jth row and jth column of the product of A and B. Okay. So then the trace of A times B is going to be, so we sum over J all those things. And then this thing that we just wrote down is K goes from 1 to N, A, J, K, B, K, J. And then since this is, so that's jth term on the diagonal. And then since this is a positive sum, it doesn't matter what order we write it in. You can always rearrange a finite sum. And I can also write those two numbers, the A and the B entries, in whatever order I want, because multiplication of numbers is commutative. So I could do the B one first. And then if you notice, this one is using the same thing that we saw before. I can observe this is the kth term on the diagonal of BA. And since I'm summing those through all k's, this is the trace of BA. So that gives it to us.